Hello there again. We're back for part 2 of the functions videos for Python. Let's jump in and do some slightly more complicated examples where we don't just have a function like this guy or a function like this guy. We've got something that's maybe a little bit more complex. So the collapse function has appeared in several of my videos so far. So let's build a function that returns the collapse sequence. I'll make my video a little bigger here. There we go. Okay, now this sort of function is not as convenient to write as a lambda function. I'm going to choose to do this as a def. Def f, oh, come on. Let's call it collapse. Let's just call it what it is. And x is going to come in, and then I'm going to do something to the x. Right? So if x%2 equals 0, that's like saying, hey, is x even, true or false? I'm going to return x divided by 2. Else, I'm going to return 3 times x plus 1. So what this does is it takes in a single number and returns the next number in the sequence in the collapse sequence. Right, so let's think about it. If I send in a 5, it's going to come in here and say, okay, well here, I would call that by saying, what is collapse of 5? Right, so when I do that, 5 comes in and it's going to say 5 divided by 2, check the remainder. Is that remainder 0? False. So I'm going to skip this line and come to this one, and I'm going to return 3 times x plus 1. So 15, 16 is what I'm going to return. And sure enough, I get 16. Or if I plug in 7, well, 7 is odd, so I'm going to return 3 times 7, 21, plus 1 is 22. Or if I throw in 8, it's going to give me back a 4. Now, this problem said, write a loop that goes through the sequence until it converges to 1. So I could say, while x is not equal to 1, colon, x is equal to collapse of x. And now I've got very clean code. Ooh, wait a minute, I need to tell it where to start. X is equal to, I want it to start somewhere, so I'll start at like 13 or something like that. Oh, and it didn't do anything because, well, I didn't tell it. I didn't tell it to print anything. Okay, so x was 13, I printed it, because 13 was not equal to 1. Then the next one was, hey, go call on the collapse function, do all of this stuff to the x, and give me back that x. And just write right over. And then keep going. So that one's kind of cool. Okay, let's make one that does the factorial. So let's remember what the factorial is. Right? If I did 1 factorial, I get 1. Right? Kind of uninteresting. 2 factorial is equal to 2 times 1. I'm using a C dot there. Oops. Here, let's format this in a nice way. All right, so 1 factorial is 1. 2 factorial is 2 times 1, which is 1. 0 factorial is defined to be 1. This is not the video to talk about why that is. 3 factorial is 3 times 2 times 1, and so on and so forth, etc. So if I put in n factorial, I'm going to do n times n minus 1 times n minus 2, and so on and so forth. Okay, so I want to define a factorial. Well, let's think about how we would do that. Right? I would like to be able to say, like, after I'm done here, I'd like to be able to say fact of 0 and get 1 back. Fact of 1 and get 1 back. Fact of 74 and have it try its best to give me the factorial of 74. 74 times 73 times 72, and so on. Well, it sounds like that's a loop. Yeah, it seems to me like that's a loop. Okay. So I'm going to do a couple things. If n is equal to 0, or n is equal to 1, I'm just going to return a 1 because I know those are both 1. Otherwise, I'm going to do something a little bit different. What I'm going to do is I'm going to take my n, so I'm going to return n times, now here's something very funky, fact of n minus 1. Let's see if that's going to work. Let's try this. So if I do n of 1, it returns a 1. If I do 0, it returns a 1. I haven't explained that line number 5 yet, but let's see if it works. If I do 2, it does 2. Well, what did it do? I sent in a 2, and the first thing, well, is 2 equal to 0 or is 2 equal to 1? No. So it skips that, goes to here. So it says, all right, I'm going to return for you 2 times whatever I get when I throw 1 less into this function. I'm calling the same function again. Well, okay, so I call 2 minus 1. So that's 1. So I call 1, that returns a 1. So this is going to be 2 times 1. Interesting. Okay, so what happens when I do 3? Now I know that 3 times 2 times 1 is 6. 6, nice. Let's see what happened. I threw in a 3. Okay, 3 is not 0 or 1, so it skipped that. And it comes down here and says, return for me 3 times the factorial of 2. Well, the factorial of 2 comes up here and says, well, okay, 2 is not 0 or 1. So 2 is going to be 2 times 1. So 3 is going to be 3 times 2 times 1. Put me on pause and go through that again, because that's a little complicated. I am recursively calling this function. So I'm calling it inside itself. So if I did the factorial of 4, I should get 24. That's 4 times 3 times 2 times 1. And I do. 5 should give me 120. 6 should give me 720. 7 should give me something big. 8, 9. This actually works super fast as well. Look at that. I've got a slick little function that will do factorials for me really, really quickly. And check this out. Oops. I like to format my code nicely so that when it prints something out, I actually get like a nice little call out to the command line that says something here. So now I can just change my n. So if I want to do factorial of 15, the factorial of 15 is that humongous number. If I try something much larger, oh, holy cow, it actually works. The factorial of 100 is that humongous number. And I don't want to push this too much. Okay, now the last one here is going to be a primality check. Now if you've already done a bunch of functions and you're happy with how functions are built, this one's a pretty complicated compared to the others. So you can leave the video now, or if you want to see the cool complicated one, let's do it. I want to see if an integer is prime. So I'm going to define a function is prime. And it's going to take a number in. And now what it's going to do is just going to check to see if that number is indeed prime. So I'm going to do a couple of things first, and then I'll go back and explain them a little bit more clearly. So primality is something I'm going to define. Primality, I'm going to say is true. Okay? And then in the end, I'm going to return primality. Okay, so right now, if I put any number in there, is prime of 4. 4 is not a prime number. It will say true. Is prime of 3? True. Is prime of 2? True. It's a worthless function. It's incorrect. But what I'm going to do next here is I'm going to say if n is equal to 1, return, oh, I'm sorry, not return. Primality is equal to false, because 1 is not a prime number. Okay, now 2 is still getting incorrect, but 1, at least it now is getting correct. I'm going to assume that n is going to come in as a positive number. Okay, otherwise, well, how do we check if something's prime? Well, if I put in like 36, I need to look through the divisors that are less than the square root of that number, pause and think why the square root would be interesting, and just check. Okay, so I'm going to write a loop for, k in the range of 2 up to, ooh boy, okay. I need up to the square root of the number. Now the square root of the number is not going to be an integer, so I should probably round that up. Ooh, so this is going to be a little interesting. So I'm going to define a new number. I'm going to call it m. It's going to be an integer. And it's going to be math.floor of math.square root of my number. Okay, so a couple things going to happen. Capital M, I'm going to send in a number. So say I send in like 6. Okay, I take the square root of 6, which is, oh, I don't know. What is the square root of 6? 2 point something, right? So little, okay. So take the square root of 6, get 2 point something. Take the floor of that, I get 2. Make it an integer. And now I'm going to do the range from 2 up to that plus 1. Now I'm doing the plus 1 because the range command only goes to 1 shy of this. So I now want to get to m. If k modular division, oh, I'm sorry, n modular division k equals 0, primality equals false. Now think about that. If I got something that when I divide, I get a remainder of 0, I must not have been prime. So I can run it. So for 1, for 2, 2 is a prime number. 3 is a prime number. 4 is not a prime number. 5 is prime. 6 is prime. 7 is, oh, 6 is prime. What did I say? 6 is not prime. It said false. 7 is prime. 8 is not prime. And why am I doing this? For n in range 100, print n equals, and then comma, primality equals. And now I can just look. Now I have a list of all of the prime numbers. Oops, I should have started at 1 because 0 is a nonsense. Okay. Oh, I could even go one step further. If is prime n, print it. Now I'm only going to print the primes. Check that out. Isn't that cool? Okay, now this is a complicated function, but I wanted to show you in the end of this video that a function in a computer science sense does not need to be just some sort of collection of arithmetic on a number. It can be a collection of code that results in something. In this case, it results in a true-false statement. Okay, I know this last one was complicated. Go play with it, go monkey around with it, make sure that it's actually going to work for you. Have some fun. See ya.